Okay, last time we talked about a top-down description of condensed matter systems or complex systems in general, and in that definition, in that description of a system, we focused on long wavelength degrees of freedom, which we call a hydrodynamic description, and we explained how it can answer certain types of questions, but maybe not others, and we discussed the question of how to construct such a description. I'm not going to go through the arguments, but the main point was that we had a free energy, which is called the Landau free energy, which is shown over here on the right. And we call it a Landau free energy, but it's not exactly a free energy at all in the same sense that the Helmholtz free energy is a thermodynamic free energy. This free energy tells you the answer to a different question. It says, if you know a spatially structured configuration of the system, I'm trying to find where I can show you this. Here we go. If you know a particular description of the system, which is coarse grains, and I want you to look over here on the left-hand side. So you've got a coarse grain order parameter, coarse grained over a scale, which I've called lambda, at every point in space R. This is a continuous function. And the question is, what is the probability of observing that function in equilibrium? The answer is given by this distribution, a Boltzmann-like distribution. But now this Landau free energy is not just a pure number. Well, it is a pure number, but it depends on the actual configuration itself. And so that is an example of a functional, and we described how we construct it over here on the right-hand side. And the way we constructed it was by using the fact that this is meant to describe the emergence of order. And so that placed very strong constraints on the type of function that you can have over here. And then we asked, how do we take into account spatial variations, at least the slow ones, the ones that are on long wavelengths? And we came to the argument that that is described by this term over here on the left, which is the lowest order term that you need in order to be able to penalize variations or deviations from a uniformity. So that's the general form of the Landau free energy, and we showed last time how it describes the qualitative and semi-quantitative features of the emergence of order, and even a little bit about the behavior of the system near the phase transition point. So what we're interested in today is to generalize this to systems with a continuous symmetry, and so this is what we're going to start off with. And then I want to go on to look at how we compute fluctuations about equilibrium. So this is something that we didn't do in the renormalization group class last quarter. This is something that is new to this class. And we're going to look at that for this class because we're going to see that the nature of the excitation spectrum above an equilibrium is different for a system with a discrete symmetry than for a system with a continuous symmetry. And that's going to help us understand the very important role played by phase degrees of freedom, and that will get us into understanding topological order. So let's get started then by introducing the ON model. So we talked about that before. So we're going to start with the Landau theory. For the ON model. Now, we talked about some models of continuous symmetries last time, and what I mean by the ON model is a model that is symmetric under orthogonal rotation group in n dimensions, but the n dimensions here corresponds to the order parameter or spin symmetry, spin space, not the real space. So this is the ON model in d dimensions, describing a system that is invariant under rotations in the n-dimensional spin space. So we're going to think of the order parameter of this in an Ising model. We would start off with just a single spin, plus or minus 1 at any site I, and that's now going to go to a vector at the site I, and that vector will have components S1, S2, S3, all the way up to Sn, and then that will be located at the site I. So I'm going to I like to use the symbol S for this. So whereas before we had I don't want the color at all. Big mistake. So whereas before this SI, when we coarse grained it, that gave us a variable which I call eta of R, and I've here denoted by lambda the coarse graining scale. So now we're going to replace this eta of R by a variable which I'll call S of R, which is the coarse grained version of this. So when I coarse grain, I get that. So what we aim to construct is the Landau theory as a function of this vector order parameter at every point in d-dimensional space R, and this Landau free energy is a scalar, and so what we need to do is to construct it. Need to consider all possible scalar quantities that we can build from this vector order parameter. So when we had a scalar order parameter, like in the Ising model, what we did was we said, well, the order parameter has to be quadratic. In eta, it has to be a quartic term, and that's how we construct the Landau free energy. So here we're also going to construct quadratic and quartic terms, but they're going to be built out of the vector order parameter. So let's do that. So the question is, what scalars can be built that are second and quartic order from the vector order parameter. And so the answer is the following. I can construct a scalar S squared, which I'm going to define as this. I take the component S alpha of the vector order parameter at the point R. I dot it with S alpha at R, and then I sum from alpha equals 1 to n, like that. And that I'll call S squared. And then I can construct S to the fourth, which is just S squared squared. And this order parameter then is by definition rotationally invariant. So both of these terms under orthogonal rotations of the spins. And these are the only two terms that I can build at this order which are like that. So then we can already see that our Landau theory is going to be it's pretty much the same as the Ising-Landau theory in terms of s squared and s to the fourth. And then we have to construct the gradient term. So the gradient term is going to be more complicated. I'm going to write that by the notation grad s squared. And what I mean by that, well, if I'm going to construct a gradient term, I have to consider the gradient with respect to the ith spatial component of the alpha component of the spin order parameter, then as a function of r. And then I want it to be invariant. So I'm going to have to take this thing squared, and then I'm going to sum over alpha is 1 to n. I'm going to sum from I equals 1 to d. So this is a generalized gradient operator, and so what these different terms mean here is here I'm summing over spatial degrees of freedom. X, Y, Z, whatever, which I'm calling X1, X2, up to XD, spatial coordinates of R. And then this is the sum over the n components of the vector S. So that's my generalization of the gradient term. Okay, so now let's have a look at what does the Landau free energy look like. So I'm going to write L is equal to the integral dr of 1/2 grad s squared plus v of s and I'm going to write that v of s is equal to 1/2 r naught s squared plus 1/4 u naught s to the fourth. So that is plotted over here on the left-hand side. So for t greater than tc, there's one minimum. And s is equal to 0. And when t is greater than tc, so this r naught is what I called some coefficient a times little t, where t is t minus tc divided by tc. And a u naught is just positive and independent of temperature. So then if I look at v of s, I've drawn it here on the left-hand side for n equals 2. And so I've got S1 on the horizontal axis, S2 on the y-axis, and up the z-axis, v of s. So you can see it's basically symmetric, like a kind of tornado or something like that. Now, if I go below Tc, then of course the sign of the s squared term changes. So at the origin, it has a negative term, and then it gradually goes back up as s to the fourth. And so the most important thing that you can see here is that there is a degenerate minimum of this potential. When we had a scalar case, an Ising case, the degenerate minimum was twofold. I had plus or minus 1. But here now we have anything on this circle. So here is the degenerate minima over here like that. So let's go back to this page on the right, and let's just calculate that. So how do we show that? Well, what we do is we compute dv by ds alpha equals 0. So I have to compute the variation with respect to any component. So alpha can be 1 up to n, and that gives me that if I do that, if I simply differentiate, then what I'm going to get is if r naught is greater than 0, which means I'm greater than Tc, then I get that S is equal to 0. If I do this when R naught is negative, i.e. T less than Tc, then if I differentiate dV by ds, what I get is equal to S alpha times well, I get S alpha times this times R naught plus U naught S alpha times S squared. That has to equal 0, and so that then tells me that I can get that S squared is equal to minus R naught over U naught. So that's the solution, and the other one, of course, is S alpha equals 0, which is the only solution when I'm above Tc. So this then doesn't specify the phase of S, it only determines the amplitude. So that direction is what we'll call phase. And so that's what I've drawn over here on the left in the red. The minimum here, this might be one solution, the one I've just drawn here, but any solution that ends on that red circle, the ground state minimum, is a solution of this equation. So the amplitude is fixed, but the phase is undeterminate. And so you have an infinitely degenerate ground state. Okay, so that's what the potential looks like. Now we're going to need to explore what are the consequences of this. In order to explore the consequences of this, I'm going to have to teach you how to calculate fluctuations. So before I teach you how to calculate fluctuations, I need to teach you how to do a Fourier transform. And I need to teach you how to do a Fourier transform so that later on you can learn how to do a functional integral. So the most important thing in doing Fourier transforms is to actually remember what a Fourier transform is and to be able to check that you've got all your definitions consistent. So I want to go through that because my experience has been that generations of classes that I've taught have in fact not been taught about Fourier transforms properly and don't know how to do the operations that I want to show you. So now we're going to talk about Fourier. Well, let me just say like this. In order to understand, in order to calculate, same thing. In order to calculate fluctuations, about a homogeneous mean field solution, which is what we've just calculated. So what we just calculated here are the solutions which are homogeneous in space. There's no spatial variation, so that's called a mean field solution. So we want to calculate the fluctuations. What we need to do is revise our understanding of Fourier transforms. So we all know the basic idea of Fourier transforms, but I want to just make sure that we've got it correct. So here are my definitions. So I'm going to start off, I'm going to go back to my scalar example for now. So I'm going to consider a scalar function in three-dimensional space, and I'm going to construct a Fourier transform of this in a finite volume of size v. So I claim that that looks like this. So that's how I'm going to define over the allowed k vectors, and we'll get on to what those allowed k vectors are in a minute. That's how I define eta of r, so of a function in a finite volume v is equal to L to the d, and d might be 3 if you want, but it doesn't have to be. Okay, so that's what I want to get out. So then I need the inverse Fourier transform, and the inverse Fourier transform is that eta k is equal to the integral over the volume integral ddr eta of r e to the minus I k dot r. So that's the inverse Fourier transform. So these two equations are the fundamental equations, and let me show you. When you've done Fourier transforms before, you've probably done this in infinite volume. So let's go and talk about how we relate this to what you've seen before. We want to talk about finite volume here because we are going to be interested in doing this very carefully and then taking the thermodynamic limit. So the volume is actually going to matter here. So that's why we're doing this in a finite volume. Okay, so the first thing you might say is, well, if this is true, then I should be able to substitute the eta of k formula up at the top into the eta of r formula on the left and see if I get eta of r. So let's just do a double check. So let's check. And I'm going to do this in two ways. I'm going to derive two consistency equations, which are very important for us to understand. So let's check. If we substitute this equation, let's call it 2, call this equation 1. Let's substitute equation 2 into 1. What do we get? So what we should get is this. Eta of r is equal to 1 over v, sum over allowed k modes. And then we're supposed to put in e to the I k dot r. And then I'm supposed to put in eta of k, and eta of k I can just read from the top here. So I can put in d r eta of r e to the minus I k dot r. Is that correct? Okay, one of you is saying yes, one of you is saying no. So I need a third person. Is this correct or not? Huh? Looks correct. Okay, so the class says it's correct. No, it's not. It's wrong. Okay, why is it wrong? Yeah. So there's a problem here, because when I write down this equation, what Julian said was this. This thing is supposed to depend on r. But if I've done it this way, then this integral, there's an integral dr on the right-hand side. So the answer won't depend on r. There's something very wrong there. Okay. What did I do wrong? It should be what?
Something any other notation for output.
Right. What you have to remember is that in this equation up here, which we just substituted in, that R could be called hippopotamus. It doesn't have to be called R. It's a dummy variable. It gets integrated over, and the end result is I get something to e to the k. So I should not, this R should not be just typographically put into this equation at the bottom here, like ChatGPT would do. It has to be done not by lexically transferring a thing by copy and paste. You actually have to realize that this variable is a dummy variable. So I should call it something that is different from R. Let's call it R prime. Like that. Okay. So what about this R, the one in each the ik dot R? Is that one correct? Why is it correct, Julian? Not sorry, not Julian. Justin. You were nodding very sagely there, so I'm asking you. It's outside the interval, yes. Remember, so that R is, you tell me what R you want, and that's the R that comes into this phase factor e to the ik dot R. So this R here and this R here are indeed the same, and the other one's a dummy variable. Okay, so that's how we have to write this equation down. So we nearly slipped up, right? So then let's have a look at this. So now let's see what this is. So I can pull the integral dd r prime out through these summations. These are finite summations. We're summing over a finite number of k values. So we're going to sum it, pull it out to the other side. And then I've got integral dd r prime, and then I've got eta of r prime. I can take that out because it doesn't depend on anything else. And then I've got all the other stuff. The other stuff depends on v, it depends on k, it depends on r, and it depends on r prime. So there's a bunch of stuff that's in here, which I'm going to write in a minute, which is, and that stuff depends on k, r, and r prime. And in that stuff, the only way that the integral dd r prime, e to r prime, can equal e to r is if this stuff is equal to a delta function of r minus r prime. Okay, that's the only way it can happen. Okay, if I integrate e to r prime with respect to times dr prime, multiply by some other thing, and the end result is I just get e to r, then the stuff that was multiplying it must be a delta function of r. And so therefore, what I can just read off then is that 1 over v sum over k e to the I k dot r minus r prime. That's all the stuff there. Just check I did it right. I did the sum over k, the e to the I k dot r, and then e to the minus I k dot r prime. So I wrote it like that. And so this thing must be delta of r minus r prime. Okay, so this is the resolution of unity, as it's called in quantum mechanics. In quantum mechanics, this would be the same thing as saying sum over bra and sum over ket n equals 1. So for those of you who've done quantum mechanics, you'll know what I mean by that. So let's just see if this thing is true. So this is the first conclusion that we've come to. So let's just remind ourselves, what do we mean by the sum over k? So what do we mean by that? Well, we have to remember that the k vector means the following. If I have a system that is described in a volume L by L by L by L, say in 3 dimensions, those allowed k vectors, if I have periodic boundary conditions, look like this. That's in d equals 3. And in d dimensions, this would be 2 pi over L n1 up to nd, like that. So that's what I mean by summing over k. I have to sum over all these integers. So these things here are integers. Okay, so now let's write down then what I mean by an integral over k. So then if I write down an integral ddk, well, what does that equal? Well, that is equal to the integral. If I wrote down an integral over volume, you'd say that's integral dx, dy, dz. So an integral over d dimensions is dx1, dx2, dx3 up to dxd. So an integral over d dimensions, but in k space, would then just be dk1, dk2, all the way up to dkd. So all the d components like that. And that would then be 2 pi over L raised to the power d, and then dn1, dn2, dnd, like that. But all of the changes in n, the n's are integers, so all of these things are just basically considered to be 1. This is just 1 to the power d. And so what that means is it gives us a rule that says that if I want to write down what the sum over k is, that corresponds to the sum over the n's. n1 is equal to 1, 2, 3, all the way up to infinity, and 2 is 1, 2, 3, up to infinity, and so on and so forth, all the way down to nd, like so. And then I can write this sum over n as basically being an integral dn 1 up to dnd. And so then because I have the relationship between ddk and ddn, what that means is that the sum over k is basically the integral ddk times L over 2 pi to the d, like so. So when I write down the sum over k, I can write that sum over k, as long as L goes to infinity, as an integral over k, and then I've turned the summing over discrete states to an integral over states which is defined as a density in k space. And so this number here, this factor, L to the 2 pi over d, this is known as the density of states in k space. So you can think of it as being something like this. I've started off in k space with allowed sets of states, like so. These are the discrete k states. And then now that we've transformed this into some smooth density, I don't know how to make it bigger. Now we have some density of states in k space like this. And this is now a smooth density of states. And to go from one to the other, I have to use this factor L over 2 pi to the d. And let's just check something here. So originally we were summing over states. So we're summing over discrete factors of e to the I k dot r, so that doesn't have any dimensions. We're just adding up a bunch of terms. So k, of course, has dimensions of 1 over length. And so this factor here, L 2 pi to the d, integral d dk, that is dimensionless. So a dimensionless sum is turned into an integral which doesn't have dimensions by the density of states in K space. So that's what density means. Okay, so why did I spend all my time telling you that? So then let's go back to this sum over here. So if I write down 1 over v sum over k e to the I k dot r minus r prime. So let's transform that into an integral. So it's 1 over v, and then I have v over 2 pi to the d integral d dk e to the I k dot r minus r prime. And so that is equal to 1 over 2 pi to the d integral over d dk e to the I k dot r minus r prime. And as I take the limit that L is going to infinity, or therefore the volume, which is L to the d, is going to infinity, what that means is that the spacing between the K states, remember that the case states are just given by this formula over here on the left. So the ends are integers. So the states differ by integers, but they're integers multiplied by a factor 2 pi over L. And as I take the limit to 2 pi over L, L goes to infinity, that gets smaller and smaller. And so what happens is the spacing between the K states goes to 0. And when the spacing between the K states goes to 0, then that means that my discrete states go to a continuum. So here on the left-hand side, this is discrete. And here I have a continuum. That's the difference between counting integers and integrating a density. So then I can now take the limit v goes to infinity. And so what I've just shown you is that the delta function, like in d dimensions, so let's call it dd in d dimensions, is 1 over 2 pi to the d. And now this is over all of space. And this is indeed the definition of delta function that you learned on your mother's knee. So everybody happy with this? Okay, so now you know now you know how we get that formula. So this is sometimes called the resolution of unity. And it's important to get that right. Now let's talk about what happens if we substitute the other way around. What about substituting equation 1 into equation 2? So let's go ahead and do that. So equation 2 was this one on the top left. Eta of k is the integral over the system d dr e to the minus I k dot r, and then I'm supposed to put in there my definition of eta of r, and my definition of eta r is over here on the left-hand side. So I can put that in as 1 over v sum over k eta k e to the I k delta r. Okay, right or wrong? K prime. K is wrong. Same reason as it was before. K is a dummy variable, so that's got to be a K prime, and that's got to be a K prime there. Okay, everybody on board with that? Okay. So now let's finish the calculation. So then what I get then is that eta of k is equal to, you can see that there's a sum over k, over k prime here on the other side. So I can pull that through. So that's the sum over k prime of some stuff times, and then I have over here an eta k prime. Okay. So what that means is that this stuff must be what? Well, I'm summing over discrete k and k prime modes. So this stuff must be what? What? A Kronecker delta. Delta of k prime. Okay, so this thing is equal to 1 if k equals k prime and 0 otherwise. Kronecker delta. Okay, so so that means we can just read off that this means that delta k prime is equal to 1 over v, the integral d r of e to the I k minus k prime dotted with r. So let's see what that means, and this is an integral over the volume. Okay, so let's just check, is this true? So if k is not equal to k prime, then what am I doing is I'm summing a bunch of terms like sine 2 pi x, or let's say x over 2 pi. So if I sum that, if I integrate that over over from 0 to 2 pi, I'm going to get the area under the sine wave. And so that is equal to 0. So I've got a bunch of phase factors that are all going to cancel. And so when k is not equal to k prime, then I get 0. So this question here is this really true? So I get 0. What happens if k does equal k prime? Then what I get is that the e to the I k minus k prime dotted with r, that equals what? Do you know? 1, exactly. Because k equals k prime, so I get e to the 0, so that gives me 1. If I integrate 1 over the volume v, I get what? What is 1 over the integral of v? Right, so then what I get is, I get 1 over v times v, and that is equal to 1. And so what I've just shown you is then that this formula is indeed correct, that this is a way to write down the Kronecker delta, right? There's one more trick. You might ask, if I have a Kronecker delta, what's the difference between a Kronecker delta and a delta function? So one more trick, there is a connection between a Dirac delta and a Kronecker delta. So why? Why is that? Why is that? So what I've just showed you is if I take the integral ddr of e to the I k minus k prime dotted with r, so that thing is equal to v delta k prime, just putting the v onto the other side. Okay, so I can write it like this. On the other hand, I know 1 over v sum over k e to the I k dot r minus r prime, that is equal to delta of r minus r prime. Okay, so yeah, what was I've lost my train of argument here. So hang on while I just get this right. So yeah, so if you look at this equation, I can swap r and space around. So the way I can write this is yeah, I'm confused with my notes here. Oh, I know. Yeah, so yeah, here's what I wanted to say. Sorry about this. So I can write delta of r minus r prime as 1 over 2 pi to the d integral ddk e to the I k dot r minus r prime. And then I can write this as 1 over v times v over 2 pi to the d, the sum over k e to the I k dot r minus r prime. So that's just substituting what's over here on the left onto over what is here on the right. And so now then I can write that the integral dd r of e to the I k minus k prime dotted with r then is 2 pi to the d times delta of k minus k prime. So this term over here is just 2 pi to the d times delta of k minus k prime. And so what I've just shown you is that if I take a finite volume and the Kronecker delta of delta k, k prime, that in the infinite volume limit translates into 2 pi to the d times delta of k minus k prime. So the two things are related through, again, this density of states in k space. And that's how you can go from a density in k space to the sum of discrete states. Notice that on the left-hand side, I've got a v here, which makes the delta function, the Kronecker delta has no dimensions. The delta function on the right, the Dirac delta, has dimensions. So this is Kronecker delta. Here is Dirac. And this equation is dimensionally correct because the delta function of k minus k prime has dimensions of length. And then it's a d-dimensional delta function. So it's length to the d, which is a volume. The v on the left-hand side has dimensions of volume as well. So this equation is dimensionally consistent. Okay, so we needed to do that. We needed to do that because now we're going to start looking at the Fourier transforms of fields and looking at their fluctuations. So now we're going to go back to fluctuations. And so here is our idea. So what is our goal? Our goal is to go beyond mean field theory. So what do I mean by that? Well, let's have a look at our potential. So I'm only drawing it in one dimension. So here is my potential that looks like this, and maybe it has a minimum at some value. So this is the minimum, we'll call that phi bar, or I prefer to call it the average of phi using these angle brackets. So let's suppose I've got a variable that can fluctuate in this potential. So what will happen is that it will fluctuate, and so it'll be going sort of back and forth like this in some way. And we want to know how much it will fluctuate. So what mean field theory says phi is equal to phi bar, always, i.e. just the average. But beyond mean field theory, what we're going to say is that phi is a random variable. And its distribution will look something like this. So here's phi, here is that mean value, P of phi. And what it actually will do is some fluctuation like that, peaked at phi bar. So that's what we expect. And so mean field theory says that the probability distribution of phi is just delta of phi minus the average. And we want to know a better approximation to that. And so that's what we're going to do next. So our better approximation, okay, this is page 73. page 74. So our better approximation is to say that that P of phi is some Gaussian centered on phi bar with some width. So what we're going to try to do is we're going to fit a Gaussian distribution around this. So that's what our goal is, fit a Gaussian to this P of phi near phi bar. So that's our goal. We want to make a probabilistic description like that. So let's just see why that might be reasonable. So let's draw a picture here of time. And here I'm going to plot phi. So what we're expecting is that there's going to be some average phi bar, and it's going to be fluctuating like that. Now on the left-hand side here, you can see that this variable is fluctuating like this. Where is it going to spend most of its time? It's going back and forth in this potential well. Is it going to be near this point most of the time? Where's it going to be most of the time? Just try drawing this a few times. Which points are getting most of the density? Say it again. Phi bar. Yes. So it's going to be. If I were to plot it as a time series, it's going to look something like this. I don't know. Right. Something like that. Okay. So I can now draw up here P of phi, and you can see that it's going to be something that looks like that, and we're going to approximate it by a Gaussian. So let's just see how we might do that. So that's the idea. So let's first of all, we're going to do this in steps. So step one, I'm just going to consider 1 degree of freedom. So we're going to say that P of some variable Q is going to be something like, or proportional to e to the minus some Q minus Q naught squared over 2 sigma squared. And I'm going to say that Q naught is what I mean by the expectation value of Q. So that's 1 degree of freedom, which I'm going to call Q. Okay. So in statistical mechanics, the probability distribution of Q would be given by the partition function, 1 over the partition function times e to the minus beta times the Hamiltonian of Q. Right? So that's what we do in statistical mechanics. So when we're going to compute fluctuations in thermal equilibrium, what do is we make an expansion of the Hamiltonian. So I'm going to write that the Hamiltonian of this variable Q is its average value, and then I'm going to do a power series expansion. So then there's going to be a term that is Q minus Q naught times H prime evaluated at Q naught plus 1/2 Q minus Q naught squared over some, well, let me write it like this. So just expanding the Hamiltonian about Q naught, and then there's higher order terms like that. Okay. So then I can write my probability distribution for this is equal to e to minus beta h of Q naught, and then e to the minus 1 over 2 lambda squared Q minus Q naught squared, plus terms that I'm neglecting. And I've written here 1 over lambda squared is defined to be beta d2h by dq squared evaluated at Q naught. And then if I have this probability distribution, then the expectation value of Q is equal to Q naught, and the expectation value of Q minus Q naught squared, that's going to be, just to expand this, it's going to be Q squared minus Q naught squared, and that is equal to lambda squared. So you have to do the integral. So I'm assuming that you know how to do the integral of Q squared x squared e to the minus x squared. Okay, so this is something that you should check. Some of you know this, some of you may not, but I don't want to just spend the time on the algebra, so just please check that. Okay, so then suppose I wanted to say, well, I want to know the free energy of this variable in thermal equilibrium. So that would then be the integral dq from minus infinity to infinity, e to the minus beta times h of q, and then that would be e to the minus beta h of q naught times the square root of 2 pi lambda squared, doing the Gaussian integral. So again, check this if you don't know how to do it. And so then what I've computed then, if I take the logarithm, the free energy then is the Hamiltonian of Q naught minus 1/2 kBt times the logarithm of 2 pi lambda squared. So that's my final result for the statistical mechanics of one variable, one degree of freedom in thermal equilibrium. So this is the value from mean field theory. That just says, you just approximate the Hamiltonian by the mean value, it's just a number, so I can just read off e to the minus f is just beta h, so f itself is h. Okay, so that's the mean field. This term over here is the fluctuation contribution to the free energy. And you can think of this as being an entropy, because fluctuations increase the entropy. You're exploring more states. So you can look at this, you can say the free energy is energy minus T times the entropy. So what I've just shown you is a kind of measure of the entropy of the system, and it comes from the fluctuations. Okay, so looking at your faces, I would say 90% of you don't know this yet, am I right? Some of you do. Okay, so for those of you who don't know this, there's a few lines of algebra that I didn't do here. So check those lines of algebra, check that you know how to do this, because it's absolutely essential for what I'm going to do next. All right, so now let's suppose I've got n degrees of freedom. Now I'm going to do this a little bit more carefully. The one-dimensional degree of freedom case is simple. Statistical mechanics of one variable, one particle in a potential well. So now we're going to consider n degrees of freedom. So now I've got Q is Q1, Q2, up to Qn. And so I want to know what is the Hamiltonian of the system. So the Hamiltonian of the system is, it's going to be expanded about the mean value, which I'll call Q naught. Oh, I want to make a point I didn't emphasize before. So let me just go back a second. Nobody asked me about this, and I was thinking that somebody was going to ask me, so I didn't mention it. But since nobody asked me, I'm going to mention it now. Why did I drop this term? If you notice, everything I did before, I used the first term, h of q naught, the mean field term, and the quadratic term. But I didn't use the first order term. Why not? What was the justification for that? Mhm. Right. Okay. The reason that we didn't use that term, I don't know if everybody could hear Julian's answer. But the reason is this. Look over here. Q naught or phi naught in this case, this thing is a local minimum. If it's a local minimum, then that means dv by d phi at phi bar is equal to 0, right? And so translate that over here, h prime, q naught we're expanding about q naught, which is the minimum of the Hamiltonian. So this term is equal to 0. So we're expanding about the maximum or the minimum, the extreme value. Okay, so the same thing is true over here. So I'm going to just write this expansion, but now I've got to write it in a more complicated way. So it's going to look like this: Q alpha minus Q alpha 0 d2h by dq alpha dq beta evaluated at Q naught times Q beta minus Q beta 0 plus higher order terms that I'm neglecting. Okay, so this now, in writing this term here, I'm going to use Einstein's summation convention. So I'm not going to be writing this in general, but I just want to remind you now, we're summing over alpha and beta go from 1 to n. Okay, and if I have repeated indices, then I'm not going to write them separately. So I'll write it this one time just to remind you, I've got alpha and beta. Those are components of Q. I'm summing over all those components. And so I can think of this as a matrix times 2 vectors. So I'm going to define I'll define a matrix M alpha beta to be D2H by dq alpha dq beta evaluated at Q naught. And sometimes this is called a Hessian matrix. And then the partition function of the system, which is just e to the minus beta f. Let's calculate what the partition function is. So it is the integral from minus infinity to infinity, product from I equals 1 to n over all the components of Q times e to the minus beta h of Q. So that's what I mean by it. Now I have to sum in, I have to substitute in this formula here. So this is going to then be the following: e to the minus beta h of Q naught. That's just a number, 17 or something like that. I just put it through the integral. And then what do I have left? I have the integral from pi I equals 1 to n dqi from minus infinity to infinity. And now I have a Gaussian term that looks like this. And I'm going to not write the components. I'm not going to write the summations. So I'm going to get that. And then what I'm going to do, so this is an integral of a quadratic form. Okay, how many people here know how to do this integral in their head? Maybe Chan does. Okay, but the rest of you are wondering what the heck it is. So the way we do this integral is we do it by making a rotation. So we do this by a similarity transformation. So what we do is I'm going to turn that into a bunch of scalars. And I'm going to do that by diagonalizing the matrix M. So how do I diagonalize the matrix M? I take the matrix M written in component notation. I take its eigenvectors, which I'll call V beta, label them by I, and then those have some eigenvectors, some eigenvalues, which I'll call lambda times V alpha of I. So this is this, so the V's here, this V I is the ith eigenvector of M with eigenvalue lambda. Okay, so I'm solving the matrix equation MV is equal to some lambda times V. That's the eigen problem. And in the way you diagonalize a matrix is you multiply and pre-multiply by the rows and columns of a matrix that is made from the eigenvectors of M. So the end result of diagonalizing is that M goes to a matrix M prime, which is now a diagonal matrix, lambda 1, lambda 2, lambda n, like this, and 0 everywhere else. And so now that it's a diagonal matrix, then I don't have any cross terms. I don't have any vector products or anything like this. So I can write the following. I'm going to define 1 over lambda squared to be, sorry, I'm going to define 1 over lambda I squared to be beta times lambda I hat. Okay, so then if I do that, then what I get is e to the minus beta f is e to the minus beta h of q naught times the integral pi I equals 1 to n d qi prime e to the minus 1/2 sum from I equals 1 to n qi prime squared over lambda I squared. Okay, so what I've done is I've turned a complicated vector and matrix operation over here. I've turned that into a sum of squares of terms. So here are my new variables. They're not the same as the q's, they're transformed. And now there's this sum over here has been diagonalized. So this is just a sum of squares. So then I can write this integral as e to the minus beta h of q naught times the product from I equals 1 to n of the integral from minus infinity to infinity d qi e to the minus 1/2 q I prime squared over lambda I squared. Okay, so look what I just did. This is now a one-dimensional integral. Whereas what I have over here is I have an n-dimensional integral. And so what I've done is because this is the sum of squares, it factorizes. And so it factorizes, so I can turn it into this product of one-dimensional integrals. And these integrals are all easy to calculate because it's just 2 pi times lambda I squared, square root. Because the integral dx is root pi. So now I can just read off an e to the minus beta f. Well, I can just read off f. So let me just write it down f straight away. So f is equal to the free energy of the system evaluated at q naught minus 1/2 kBt times the sum from I equals 1 to n times the logarithm of 2 pi lambda I squared. And those lambdas are obtained by taking the eigenvalues of the matrix M, and the matrix M is this Hessian matrix obtained from the Hamiltonian. So this is how you do statistical mechanics of n degrees of freedom. Okay, and we don't care about that. What we care about is what you do when you have an infinite number of degrees of freedom. Okay, so what we want to do, so the next thing, statistical mechanics of the fluctuations of an infinite number of degrees of freedom. And that's what's known as field theory, statistical field theory. Why a field? Well, if you have a variable that is a continuous function of a variable like space, it's called a field. And now we're trying to do is what are the fluctuations of a field, like the electromagnetic field or the gravitational field or the order parameter in a superfluid. We want to work out what are the thermal fluctuations of that. So I'm not going to start that today. So let's leave it like that. But what we're going to essentially do next time is we're going to take the results that we've just obtained for n degrees of freedom, and then we're going to look at what happens when we take the n goes to infinity limit. So that's the basic mechanism. And we're going to do the calculation by taking our system, which is a field, and what we're going to say, if I've got a field in a volume V, I can write it down as a bunch of Fourier components. Once I've got a bunch of Fourier components, I have a discrete set of Fourier components. So if I've got a discrete set of Fourier components, then it's like this integral that I've done here, where I've got a discrete number of degrees of freedom. So now I can do my functional integral, my integral over the fluctuations of a continuous field. What I do is I just calculate the fluctuations for the Fourier components, and then I take the thermodynamic limit, and those components then go into functions. And that's why, to do the mathematics of that, that's why I spent all this time working for you how to do a Fourier transform and looking at what happens to a delta function, in a discrete delta function and a continuous delta function, and being able to go back and forth between discrete Fourier transforms and continuous Fourier transforms. Okay. So we're not going to start that today, but we're going to start that at the beginning of next lecture. And then what we will do on the next lecture is we will then use this algebra to then go and instantly compute the correlation function in fluctuating systems. Now, why are we doing it this way? Okay, there's a reason. And I want to tell you that reason, and then we'll finish. The reason that we're doing this is that there's something special about systems which have got a Gaussian Hamiltonian. So imagine here, I've got a Hamiltonian which is a Gaussian. So I've got it over here. Where is my Gaussian Hamiltonian? This one. Okay, here is my Gaussian Hamiltonian. So look over here on the left. It's Gaussian, meaning it's quadratic in Q, about its mean. So it looks like a harmonic oscillator. So harmonic oscillator, mean position is Q naught. Okay, when I do the integral of that for the partition function, I'm doing a Gaussian integral. There's a special theorem for systems which have Hamiltonians with quadratic degrees of freedom. There's a special theorem in classical mechanics. Anybody know what it is? So if I ask you, what is the contribution to say the heat capacity, or the contribution to the free energy of a harmonic oscillator from its fluctuations? What is the answer to that? It's a very classic theorem in statistical mechanics. And I'll prove it to you next time. It's called the equipartition theorem. Okay, it says that every quadratic degree of freedom in thermal equilibrium has what? Speak up louder.
1/2 kBT.
Half kBT for what? And that's a contribution to what quantity? Well, the energy, I don't care about energy. Right? So the theorem says this: if I have a quadratic degree of freedom, say a half k x squared, then the expectation value okay. So we'll do this next time. Okay. We'll do it next time. Anyway, before next time, in today's lecture, I went fast through a bunch of algebra. Okay. Normally I would go much faster. But for this class, well, I know you haven't had this before. I filled in more steps. The places where I said check and check, please check them. It'll only take you 5 or 10 minutes at most to do those checks. I want to make sure that you understand those things. And then the last thing is look up the equipartition theorem of energy and make sure that you know what it is, so that when I ask you about it next lecture, you all know it, because that's going to be a quick trick for computing correlation functions, which would otherwise be very complicated to compute. Okay, so that's the end of today's lecture.